Okay, so Sarfaraz, if you see somebody waiting in the queue, just let them in while I introduce.
Okay, sure.
Okay, welcome back. I'm Nadimul Faisal. This is round 5 of METASIS webinar. Today, presentation is from Professor Mamdud Hossain. He'll be talking on levelized cost of electrolytic hydrogen production in Scotland. So Mamdud is a professor of future energy. He's a lead of energy research group looking after a large group, which is around 10 academic and 35 PhD students. He is also team lead for hydrogen and advanced fuel as SPD, which is an organization based in Scotland. His expertise in computational modeling, electrolysis, tidal wave wind energy systems, including multi-phase flow in oil and gas sector. He has worked on multiple funded projects from EPSRC, OGTC, NZTC, SFC, and others. He's a senior fellow of Higher Education Academy, a chartered engineer, and also very active member of IMEKI. In terms of housekeeping, we'll be recording this session and we'll provide you the YouTube link once available. We will take the question and answer question toward the end of the presentation. And then, however, you feel free to put your question as the presentation continues. So without further delay, may I invite Professor Mamdud to share his slide, please. Thank you.
Good afternoon. I hope you can hear me.
Yes.
And see the slide. Today I'm going to talk about techno-economic assessment of PEM green hydrogen production. We are looking at different electricity supply pathways and looking at this pathway, how we can reduce the price of levelized cost of hydrogen production. Just want to say a little bit about this project. First of all, I am not an economist and I am not a expert on electricity pricing policies. Okay. So these are the two big things. I am actually a mechanical engineer and my expertise in technology development. But I got interested in this economic aspect of green hydrogen production and looking at it, how far we can reduce the cost to make it more cost effective. And then I started looking at electricity supply and how the pricing work. But these two areas, I have no expertise. So if you have any questions, probably I will have to refer to somebody else. Having said that, let's look at why is the motivation for doing this research. Number one, hydrogen. We have been talking about hydrogen for a long time, and we know that hydrogen is going to play a big role in different aspect of industrial decarbonization, long duration energy storage, sustainable fuel, and offshore energy system. Uh, uh, I mean, initially we talk about hydrogen. It can be used in any sector, in many different way, and thinking as a one of the silver bullet that will solve our net zero achievement. However, later we found out that it's not the case because of this price of hydrogen. The green hydrogen production cost is very, very expensive. Why? Because it depends on electricity consumption. About 60 to 80% of hydrogen cost is coming from electricity. Initial understanding and initial thought was that electrolyzer, which used expensive materials, had something like platinum, something like YSZ, something like novel material, GDC. So, because of those material costs, hydrogen production is very expensive. But if you look at more carefully about the whole system, it turns out to be hydrogen production cost is dominated by electricity. So hydrogen source selection is critical to achieve low cost hydrogen, how we are going to get electricity from and how we are going to use that electricity. So that was my motivation to do this research. Though again, disclaimer is that I am not expert in economics or hydrogen or electricity pricing. Having said that, main research question I'm going to talk about is what are the choices we have from electricity supply pathway, how they can influence levelized cost of hydrogen production, what is the utilization factor of electrolyzer and how we can improve utilization factor, and coming back to economic competitiveness of hydrogen production. Specifically, I'm going to look at different type of electricity supply, something like grid electricity. Then we are looking at wholesale electricity market. We have offshore wind power purchase agreement, onshore wind power purchase agreement, and curtailment derived electricity, and then whether we can have a hybrid electricity system that can allow us to reduce the cost of hydrogen production. Okay, so how we are going to do that in terms of methodology? I have used a very simple methodology, which is starting from electricity source. Okay, and then start with electricity source. We are looking at PEM electrolyzer, and within the PEM electrolyzer, how much annual hydrogen can be produced from electrolyzer, and then its economic assessment, and finalize to compare different pathway of hydrogen production or electricity supply. We convert everything in localized cost of hydrogen production. Sorry, levelized cost of hydrogen production. So there are much more complexity here. We have storage system, we have a transport system, we have balance of plant system. Those are complexity I am not including in my analysis. So basically, to do that levelized cost of hydrogen production, we are looking at capex, we are looking at operation cost or opex, electricity price and water price are divided by hydrogen, total hydrogen production. How much will be the cost per kg? Okay, on of the area that we have to make some assumptions to do the calculation is that we are looking at technology called PEM electrolyzer. Now, under METASIS, jointly led by RGU, Surrey, and Aston University, we are actually developing solid oxide electrolyzer, which under the development is not is still commercially not available that much. So I have looked at PEM electrolyzer as the basis of this calculation, but we can use solid oxide electrolyzer or any other electrolyzer. We just need to change these values and things like that. So some of the assumptions is that this PEM electrolyzer will last 8 years, and after that you have to change the electrolyzer. However, the total project life is 20 years. And if you are investing money, capex, we are thinking that there is a discount rate of money of 8%. That means whatever pound we have today, tomorrow the price of the pound or the purchasing power of the pound will go down. So at a rate of 8%. Capex, we are considering 900 pound per kilowatt of PEM. This is actually very, very optimistic number. This number can go as high as 2000. But we are, I'm taking a very, very optimistic number. Maybe this value is still not available in the market, but let's see what happens. OPEX cost, we are assuming that 4% of the capex is used for operating cost per year, which include maintenance and servicing and other thing. It also take into account 8 years lifetime. So when you make a change of that after 8 years, when you change the stack, that price is also included in the modeling. What I wanted to look at is specific energy consumption. How much energy is required to produce per kg of hydrogen? This number 50 is highly efficient PEM electrolyzer with a efficiency of I think 55% to or 60%, something like that. If you use solid oxide electrolyzer, that number can go up to that can actually get reduced significantly. Per kg of hydrogen production with it, solid oxide electrolyzer will be lot less, will need less energy. So bear in mind, this 50 is the kilowatt hour energy required to produce per kg of hydrogen. Water consumption, I have taken 9 liter per kg of hydrogen. This is again optimistic number. This number can go up to 20. We are assuming stoichiometric chemistry. So whatever steam we are putting in is or water we are putting it is completely converted into hydrogen. But as I said, that number can be twice as much. This is the capital recovery method. That's the standard calculation based on discount rate of money and also 20 years of our project life. And also we include, we stack replacement after 8 years. So basically this type of capital recovery method gives you a realistic life cycle costing. So you're spending 900 capex, 900 pound per kilowatt, that is spent over 20 years. So the value of money goes down. So this is the standard way of ensuring we have a realistic costing over 20 years time period. Okay, now look at electricity, where we can get our electricity. First of all, we have a supply model, grid connected, grid import. So if you have an industry, if you want to take electricity, buy electricity from off the grid for industrial supply, the price vary widely from 120 pound to 250 per megawatt hour. This is the industrial grid price. However, if you pay that price, you have your electricity available all the time. Utilization factor 0.9, we can go up to 100% of the time because 24 hours in a day we have our electricity. Then there is another way of buying electricity, which is called wholesale linked electricity price. This is very, very volatile. This price changes every hour. Okay, and that price surprisingly can go up to 350 pound per megawatt hour, or it can come down to 0 and things like that. So you say this is a very volatile market. Every hour it changes. You can have an agreement saying that, okay, I will buy from the wholesale linked at a price of 100 pound per megawatt hour, but when the price goes up, you don't buy. So your utilization factor actually goes down because you are not buying when the price is high. That is not economical to buy price. So you only buy price when the price is low. So hourly price fluctuating, and you are only buying when you have low prices. So that means your utilization factor is low. You're not getting electricity all the times around that price. Price goes up, you don't buy it. You can have a long-term contract called power purchase agreement directly with the offshore wind company. This is a long-term. You can get a favorable price of 60 to 90 pound per megawatt hour. In North Sea, utilization factor is 0.5. What it means that wind doesn't blow all the time. Okay, wind doesn't blow all the time. We know that during summertime, wind blows less. During winter, wind blows more. And so we only get electricity 50% of the time at this price. Similarly, onshore wind is actually less utilization factor. Okay, price is a little bit low. You can have a power purchase agreement with onshore wind supplier. Price is 50 to 80 pound per megawatt hour, but you get only 40% of the time this electricity is supplied. Good news is that you have seen a lot of time wind is blowing, but wind is turbine is not rotating. wind is blowing, but wind turbine is not rotating. These are switched off because we have excess amount of electricity in the grid, so these are not supplied. We also heard the story that plant owner are paid money to switch it off. They are paid money to switch it off. So you can get this curtailed electricity free, okay, or maybe 20 pound per megawatt hour, okay, and you can negotiate, as I say, a free deal also. Downside, that curtailment only happen 20% of the time. 80% of the time you don't have this electricity available to you. It's a low price, but utilization factor is 0.2. Okay, maybe 0.3. We can also have a combination of wind and grid connected or wholesale connected. So you can if you have an electrolyzer plant, you can have your electricity supply from different sources also combination of sources, and that can give you a utilization factor of 0.8, as high as 0.8 or 0.9. So why I'm interested in utilization factor? Why I'm focusing on these numbers here, not only price, but utilization factor. I'll show you in the next slide why it is important. Okay, so if you look at the hydrogen production, how much hydrogen produced annually, so you have a specific cost of electricity, consumption, specific electricity consumption. If I go back to there, specific energy consumption, that means how much kilowatt hour of electricity you need to produce 1 kg of hydrogen. This 50 kilowatt hour. But that kilowatt hour, then I converted that into in 1 year we have this amount of hour, but not all of those hours you can produce electricity, hydrogen, because we don't have the supply of electricity. We don't have supply of electricity. If it is grid connected, our utilization factor is 1 or 100%. In our calculation, we are taking 0.9. Maybe there will be some downturn in your plant and things like that. Whereas if you use the curtailed electricity, this utilization factor may be 0.3. So though you have your electrolyzer capacity, it only takes 50 kilowatt hour of electricity to produce 1 kg of hydrogen. You may not have electricity supply throughout your 24 hours a day, okay, or throughout 8,760 hours in a year. So this is often a dominating factor, utilization factor. It increasing utilization factor. You have a high value, you increase hydrogen output. You reduce capex contribution per kg of hydrogen because you invested a lot of money. You want to use that electrolyzer 24 hours a day. Continuously you want to use it. If it sits idle, you lose your utilization factor. Your money is gone. It's sitting there idly. And this utilization factor is a dominating factor in our economic parameter, how you price the hydrogen production price. So now to calculate levelized cost of hydrogen, cost component, what are the cost component? Electricity cost, capital cost, we have capex, that is annualized capex, because we have this recovery factor of money investment. If I look at that, annualized capital cost, so we have included capital recovery method is 8% interest over 20 years. So annualized capex of hydrogen, we can convert that. Operating cost is there, and then cost of water, and of course cost of electricity. Okay, so water cost is also included. If you include everything and then run it, levelized cost of hydrogen calculation is a simple calculation based on this algebraic equation. It's not a complex calculation, okay? So if you have a simple algebraic calculation and look at the number, then you see levelized cost of hydrogen, how much pound it need per kg of hydrogen production, And if you look at grid, price is more than £10 per kg, wholesale linked about £6, offshore wind PPA here, onshore wind PPA. These are power purchase agreement you can make with this offshore electricity producer or onshore electricity producer, curtailment based. So that was looking really attractive because we get a free electricity and you turn out to be price is very expensive, about less than 10 pound per kg. And also if you have a hybrid system, then you price is about 8. So basically, if you think about the target of £2 per kg, none of these actually meeting, nowhere near £2 per kg. Where is this £2 per kg coming from? These are the target set up by different body. I will come to that in a minute. Just for reference, if you look at the gray hydrogen, hydrogen is still produced using steam reforming, very established technology, which is used in industry. And also, if you look at the price of levelized cost of hydrogen production through your steam reforming, the price is actually £1 per kg. Okay, so that's the situation here. If you look at the ranking, wholesale linked electricity, wholesale linked electricity, if you can buy that, then is the cheapest option, £6.22 per kg, and expensive is directly getting electricity from your grid at an industrial rate, which is 11.31 pound per kg. Offshore wind, we talked about offshore wind quite all the time. Idea is to link up hydrogen production with offshore wind, but the price is 7.45 pound per kg. Curtailment, we talked about curtailment also, because offshore wind, we may use that curtailed energy which we get free. Still the price is 9.71 per kg. So closest to 2 kg target is actually, if you can have a agreement with your supply and buy it with the random variation of wholesale link price, probably you are better off producing hydrogen at 6.22 pound per kg. So what are the advantage and disadvantage into different supplier of electricity? So if you think about grid electricity, which is expensive, however, you have a utilization factor of more than 90%, and you can run your electrolyzer continuously. Okay. However, downside is high electricity cost. Result, electricity price dominates levelized cost of hydrogen. Okay. Curtailment electricity, on the other hand, it is attractive. We may call it a free electricity. Potentially, we can get electricity less than £1 per kg. However, utilization factor is only 20%, leading to poor asset utilization. If you have a curtailed electricity, maybe you can increase the utilization factor a little bit from 20 to 30 or 40, then you have a better price. Okay. So what do you do? Offshore wind power purchase agreement is a long term, certainty is there. You have a moderate electricity cost, moderate utilization factor, long term price certainty. So we talked about offshore wind power purchase agreement, the most bankable hydrogen pathway. That was the discussion now. And if you can then increase the what do you call it, utilization factor, maybe with battery, maybe some other storage facilities, maybe you can improve the utilization factor a little bit more, and then you can produce the hydrogen at a cheaper price. We did a sensitivity analysis to look at really whether we can get down the price by changing all other parameters. So on the one scale, you have a utilization factor. On the other scale, you have electricity price coming from offshore wind power purchase agreement. And through that, as I said, if you can increase that utilization factor to 90%, which is massive actually, and if you can reduce the price of offshore electricity generation, if you have a favorable contract, reducing up to 40 pound per megawatt hour, then maybe you can reduce your levelized cost of hydrogen production to 4 pound. It's still very high. And this 90% utilization is still difficult to achieve. We are at 50% at offshore wind. So that's, and the price we are looking at here, we have to significantly reducing the price of offshore wind. You need to get a really, really favorable power purchase agreement with them. So why a 20 pound per kg boundary? Why we are looking at? This is the target set up by often UK Hydrogen Strategy, EU Hydrogen Bank, Hydrogen Council, lot of people and even developer saying that we can produce hydrogen at 2 pound per kg. A lot of technology developer actually claiming this number, which is actually very difficult to achieve. Okay, so we try to do more sensitivity analysis. Okay, let's make electricity price 0. Bring the line down, further down, maybe up to 10 here, 10 pound. And utilization factor 0.9, extreme case. Maybe we can hit 2 pound per kg, maybe 100% utilization factor or 95, and reducing the electricity price as down as 10 pound per megawatt hour. Okay, industrial price actually 210 pound per megawatt hour. Yes, 210 today. Bring it down to 10. Okay, let's play with the utilization factor again. Utilization factor has a big impact, but early on, from maybe from 5% to 20%, 30, 40%, it brings down the levelized cost of hydrogen rapidly, and then it flatten up here. But still, we are not meeting the target of 2 pound per kg by changing the utilization factor and keeping these prices of electricity from 200 to 20 megawatt. This is really, really low curtailment domain. So now what I did, I looked at all single parameter, including capex, because all other analysis before kept the capex price at 900. Now let's vary the capex price from 600, reduce it down to 1300, and distribute it randomly along our average price of 900 with a standard deviation of 120, and let it clip between 600 and 1300. Don't let it go below 600 or above 1300. This is our average price. This is our standard deviation. Capex. It can go down to 600 if you have supply chain, if you have learning from our scaling up and things like that. From 900 pound per kilowatt, you can bring it down to 600 or even less, maybe 30 years into the future. Electricity price, again, look at from 0 to 200. Vary the utilization factor from 95% and from 0 to 5%. Very low, very high. And those we mixed up independently, randomly with a Monte Carlo simulation, and then see what's happened, how is our distribution of price of levelized cost of hydrogen. So you can see that the mean cost is 8.18 kg per, sorry, 8.18 pound per kg mean levelized cost. We want to hit the target 2, still we are not meeting the target here. The best case scenario is 7.56 kg, sorry, 5.32 kg. There is a 10% probability of reaching there. Or if you look at the worst case scenario, 90% probability of keeping your price 10.94 kg or below that number. So that's the higher end. This is the lower end. What is the probability of achieving 2 pound kg? 0 under the current setting. Even in the future setting, because we have brought down our capex of electrolyzer further down here. So that may be into 10 years with our economic and scale and learning from doing a lot of project, optimizing the supply chain and things like that, is still reducing the capex cost and things like that, still we are not meeting 2 pound per kg. Water price, that is included. I haven't looked at water price, to be honest, at all, because we know that water cost is simply maybe 1/100th of the cost. So I didn't play with the water cost. So the main factor is electricity price and utilization factor. We can get free electricity, 0. Utilization factor is low. You get expensive electricity, utilization factor may be 100%, but still it's not helping us to reach our target of 2 pound per kg. So what can we do? So best case scenario will be, we run further optimization actually. Best case scenario will be reduce the electricity price up to 10 megawatt per hour, increase the utilization factor 2.95, and we can get up to 2.45 pound per kg here. Okay, so you now see the challenge of economics of electrolysis and how we can reduce the cost to make it more cost competitive. So the key driver, the economic driver, is actually electricity price and utilization factor. There is a modest effect of capex, how much capex we can reduce. In our calculation, capex is actually very, very low, only 900 pound per kilowatt of capex price of PM. Actually, in the market, it could be 2000, to be honest. And we also did the analysis based on 600. So optimistic scenario will be electricity price. We can get it down to 10 megawatt per hour, curtailed electricity, we call it, or something free, but utilization factor then become a big issue. So you have to have a very low price of electricity, high utilization factor. You have to have this electricity 24 hours. Impact of capex is very, very moderate. So learning from our experience, trying to reduce the price, optimize the expensive material, platinum and things, probably only help us so much. And water cost, almost negligible, to be honest, within the whole system. So what you can do for Scotland? We have exceptional offshore wind resource. We have significant wind curtailment. We have hydrogen export opportunities. So we have to find a most promising pathway, which could be hybrid system combining offshore wind, curtailment, grid support, combination of these, because we need to increase the utilization factor. That's why grid support is there. You need to have a favorable pricing. We have to lobby the government that our renewable energy price should be linked with maybe the capex of renewable energy, not linked with the market value of oil and market value of the gas. I think my understanding is that electricity price is linked with market value of the gas. So volatile market, it goes up and down, and that price also goes up and down with even renewable energy should be free. Of course, we are investing capex, so we have to recover that. So if you have a promising pathway to look at, we have to look at some sorts of hybrid system, offshore wind, as I said before, curtailment, because there is significant curtailment in Scotland. If you can use that utilization factor here, and somehow grid support, cheap price of the grid electricity somehow, then only then we can have a reasonable price. But still, is actually electricity price is strongly determining the levelized cost of hydrogen. And then second important factor is utilization factor. So curtail electricity offers low cost energy but poor utilization. Grid electricity offers high utilization but high operating cost. Maybe we can get a favorable purchase agreement with the offshore wind with some source of cost utilization balance, hybrid system. Then and only then we can have a competitive green hydrogen production in Scotland. So that's where I conclude. As I said again, I am not economist and I am not a electrical price setter, or I don't have the expertise of how these prices are set. I just took information from different sources, put it in the model to see whether we can hit 2 pound target, and is still a situation is really complex to hit a 2 pound target. Thank you all.
Thank you, Mamdud. That was very insightful. So we have got, while we receive more questions from the audience, feel free to put on the chat function. So there are a couple of questions, one from Dr. Bahman from Surrey. So Bahman is asking, is further improving electrolyzer efficiency, for example, steam, is less important than improving access to low-cost renewable electricity? Mamdud.
Yes, but it will be nice if I repeat the calculation, because for the time being I'm using a 50 kilowatt hour per kg of hydrogen. That is coming from Nernst equation and things like that, and also efficiency of a PEM. For solid oxide electrolyzer, that value could be 35 or something. And so I need to repeat the calculation, to be honest, and then I can conclude. Here is the calculation. That I was talking about is this number. For solid oxide electrolyzer, that number will be low. This number 50. So then, this capex will be higher for solid oxide electrolyzer. And Faisal, you are talking other day, you said something like 5,000 pound or something.
Yes. As part of the METASIS, we have to look into the pricing of what we are doing. So, yeah. So the other question from Abdullah is if you have done any analysis on alkaline or other competitive technology and how METASIS can address the challenges in PEM electrolysis.
Okay, I haven't done alkaline. Obviously, alkaline is cheaper than PEM electrolyzer, but I have put a very, very favorable price of 900 pound per kilowatt of capex for PEM. I think this price is actually for alkaline rather than PEM. If you do a Google search, you will find PEM capex is maybe 2,000, alkaline is about 900, 2,000. So I intentionally took a very favorable number to see whether we can meet 2 pound target. So alkaline probably if I repeat this calculation with a realistic alkaline price, it probably will not be making much difference.
Sure.
But for solid oxide electrolyzer, as I said, we are more hopeful because it doesn't require that much of electricity. It requires less electricity, more heat. And the material cost of solid oxide electrolyzer, my guess is these are cheaper material compared to PEM material, which involve platinum, whereas in solid oxide electrolyzer, we have slightly cheaper ceramic material. So,
Indeed,
yeah.
Thank you. So, yes, Abdullah, we will share you the recording of the presentation today. I've got a few questions. So,
Sure.
based on your current analysis, you said that electricity is one of the important barrier. So the only option left is we design electrolyzer which doesn't require electricity at all.
Yeah, solid oxide electrolyzer, which needed electricity, but with a less what do you call is less electricity, more heat. But I don't know the price of solar energy compared to offshore wind. My guess is that solar energy will be a lot cheaper. And if you couple it with solar energy, might be able to produce cheaper hydrogen.
Sure. So
I can repeat the same calculation based on solar energy prices.
I think that will be good if you also include other data for various electrolyzer and see the variation.
Here, yeah. Solar energy price, if you can add it, I think it will be interesting to look at it also.
Sure, thank you. So there are two techniques which I'm aware of. One is called thermolysis and also photolysis, which doesn't require electricity. But I understand the technology readiness level is around 1 or 2. It doesn't require it. So that may be a couple of options in terms of methodology of splitting or steam or water into hydrogen oxygen. So the other question I have, you have set 2 pounds per kg of hydrogen. I believe these are some government policy and guidance. Now,
ultimate target.
If we compare with the other energy vector, for example, petrol, so average price these days around 1.5 pound per liter. Yes, and any changes happen globally, the price goes up, I believe, because of the supply and demand issue. So do you think that the 2 pound which has been set, is that the wrong number? Why we have to fit to consider 2 pound?
Okay, that's a good question. And I think that is related with the gray hydrogen that is produced at 1 pound now per kg. So if you look at the different technology comparison, that's where it is. So gray hydrogen is produced at 1, so green hydrogen maybe 10 pounds. So bring it down somewhere to 2 pounds. But if you're right, if you look at the energy security point of view, yeah, 10 pound may be okay. If you think about long-term security, then 10 pound is maybe okay. I don't know. Energy security, where market volatility is very high, you are saying. So, but then many of these electricity price can be have some incentive for hydrogen production. If the government come up with a policy of hydrogen, you can get really cheap electricity for hydrogen, then that can be done.
Indeed. So I think we have to reach out to stakeholders to find out the issues with the electricity costing and the challenges within that framework. Otherwise, it is not going to come down as low as 2 pound per kg.
Yeah, but what is the price we can be commercially viable? That's the question. So
Indeed.
if we are happy with 5, we can easily meet 5 pound target.
Indeed. So there's another question from Abdullah. How far are we from getting cheaper hydrogen in Scotland?
Cheaper means we can produce hydrogen now. It depends on what is the electricity price we are going to pay. Because PEM and alkaline is already in the market. We can buy big plant, megawatt size plant. So it's about coupling up with the electricity and then producing. So if we take the alkaline technology, which has got a lower, I think, current density, so it is less efficient in hydrogen production. But yeah, we can produce at a reasonable price.
Okay.
The challenge is when I spoke with other stakeholders, there are a lot of initial enthusiasm for hydrogen production, and there is a lot of funding which is called HAR, Hydrogen Allocation Round 1 and Hydrogen Allocation Round 2. They paid money to come up with a big project for hydrogen production. But now they found out that there is no off-taker. Nobody is buying hydrogen from and utilizing that hydrogen. So there is the challenge now, how we can create a market. So whatever hydrogen you produce, you can sell it.
If we make the cost of the electrolyzer very low,
Yeah.
do you think that will help?
I can repeat the calculation. I have reduced it as low as 600 pound per kilowatt. I think that's a very reasonable price. We cannot reduce the price there anymore. Only thing we can do is getting cheap electricity 24 hours. We can get cheap electricity, but not all the time. That is the issue.
Indeed.
Yeah.
So I think there's a lot of challenges and barriers which we have to address. Thank you very much. So I have got one announcement to make for our audience. Our next webinar is on 27th of August. I'm just sharing the registration details. So feel free to register for that. And also, I'll send you the recording of this presentation as soon as it is available. And so there is another question which has come along from Muhammad. Can this calculation be shared open access in a form of Excel sheet?
I have done it with the Python code. So if you want, I can share it. Yeah, it's nothing hidden there.
That will be great. Thanks, Mamdud. Any final question
So
or comment?
what will
from
be the
anybody?
mode of sharing, Faisal?
If you share me the Excel file or whatever format, I can send them via email.
Okay, that's good.
Right. So if there is no further question or comment, we can give it a closer, and we look forward to the next webinar, which will be on 27th of August. So that will be from Professor Sudhasatva Basu from IIT Delhi, and he'll be talking on some different challenges and materials in electrolysis. Thank you very much.